Hello students, as we are done with the frequency hopping code acquisition technique for frequency hopping spread spectrum receiver, today we will discuss about the frequency hopping spread spectrum communication tracking mechanisms inside the receiver. Like direct sequence spread spectrum communication, here also the tracking is performed after code acquisition is done. I mean the code alignment, course alignment is done by any one of the three techniques that we have discussed, and then we really understand that there is some residual code error, residual offset is there, and we are by means of tracking we will be trying to correct that, and we will be trying to continuously keep on monitoring the phase offsets that are happening in between the incoming signal and the locally generated sequence time to time, and if some offsets are there, we will try to correct it within the range of the operation. If the correction is not sufficient to bring them align them again, then it is a job of the tracking circuit that he will trigger the course alignment once again, and because if it goes beyond its correction range, it will trigger the tracking code acquisition once again, and then code acquisition output of the code acquisition will be fed again to the FHSS tracking network. So, the goals are two types, goals are of twofold. The first one is actually to maintain the code synchronization, both the coarse as well as the fine, and in addition to this, if the coarse synchronization has established a track incorrectly, always incorrectly already it is, the second goal of this tracking mechanism is that he will recognize this, I mean identify this, and return to the course synchronization as quickly as possible. So, turn on the course synchronization as fast as possible. So, he is actually doing a very crucial job. Whether the course acquisition is also done perfectly or not, that is checked first inside the tracking mechanism and in the tracking circuit, and then if it is not done properly, then he will trigger the code acquisition once again, and then if it is done correctly, then he will enter into the second phase. Perhaps the most common architecture of this FHSS tracking is based on the early late gate, and the early late gate circuit. This is the circuit where actually the FHSS tracking goes on. Remember, there is a early gate generator. Do you remember? Hopefully you will be remembering that we had a early gate generator in the DSSS hopping tracking, and also we had a late gate generator in the DSSS tracking. So, similarly here also we have a early gate generator and a late gate generator in the circuit. And if there is a perfect synchronization with suppose with early gate, and remember this code generated is generating the chip for half of the chip period, and late gate generator is generating for the remaining half part of the chip. For suppose example, if this is the total duration of a chip, early gate will be generating with the perfect synchronization sequence, synchronization point. Early gate will be perfectly generating a chip for the half of the period, and late gate will be actually generating another chip for the next half of the period. Clear? So, given that it is TC, so TC by 2 is taken care by the early gate and the late gate. And if when they are synchronized also, so the early gate output, this integrator output, so after this multiplication and the bandpass filter, when this integrate, it enters into the integrator for the early gate generator. This integrator integrates for a period of the first half only, and it generates an output called G1x. Now, remember, if they are in the perfect sync, no, then the integrator output slowly grows up and it reaches maximum at the end of the TC by 2, and it remains at TC by 2 for the rest part of the chip duration. So, what is happening? It is we will explain it in the diagram next. So, I am told that it is this is the whole chip duration TC. So, for perfect synchronization case, for TC by 2 times you are having the gate have generated the pulse for the early gate generator. If I filter this signal output, so for this it will be filtered out, and then here the signal will be now integrated. So, integrator will integrate, and slowly if I integrate a square wave, so slowly it will be integrating, and actually it will give me a sawtooth wave kind of. And then after, at the end of this TC by 2, when this early gate output is coming down, then the G1x will constant hold this value of this integrated output till the end of the chip period. So, this is the situation. So, similarly, if I look into the late gate generator is like this. The late gate generator output actually comes for the next half of the TC by 2. So, it is TC by 2 to TC, it is a late gate. And if I look into that late gate is getting multiplied, this signal is getting multiplied with the signal, incoming signal. Band pass filter has passed it, I mean it is filtered it and fed it into the integrator. Integrator is integrating it for the next half of the signal. So, the integrated output, if this is my G1x, so G2x will be actually giving me an output like this, and actually both of them are coming down. So, he will come down. So, G2x is like this, will show me the output like this. So, this is the way the upper path and the lower path is working in the early and late gate tracking loop circuit. So, after addition what is going on we will discuss in the next timing diagram, but this is the fundamental work that is happening into the whole circuit. Remember where from this PN sequences are getting generated. So, there is a common source of the locally generated random sequence, and that is fed both through the late gate generator as well as the early gate generator. And early gate generator, late gate generator, according to the trigger coming from the PN sequence generator, they are generating their corresponding sequences with respect to the TC by 2 of duration of TC by 2 with a gap of the TC by 2 also from each other. Okay. And remember what is happening if we understand like this. So, this was the early gate half TC by 2, this is TC by 2. So, let us start the explanation once again. Here I draw the figure like this. This was the TC, this was my TC by 2 period, this is another TC by 2 period for the late gate. G1x or G1t, it will be integrating like this, and it will be holding good, and then you are having the next one, and then you will be having the next one, and then at the end actually it will start integrating from here, and at the end it will be having the maximum peak, and the same value is hold till the end of the TC. And for the lower one it will start at this point, the integrator output will start integrating at this point, because here is the start of this pulse. So, he will start at this point, it will end, it will be having a peak value, and it will come down, because at the end of the TC everything is coming down. Now, at the output of this G3T, let us go back and visit where this G3T is. G3T is here, that means output of this G1 and G2x is getting added and get fed, and this other output is getting fed into the voltage controlled oscillator block. So, if I now add these two signal, what I should see when they are perfectly synced with the incoming signal. So, the output of the adder will start from here like this, it will reach the peak. After that, this is the negative voltage going up. So, the adder output will come down, and exactly in the perfect sync position it should come down to 0, because the voltage, positive voltage is equivalent to the negative voltage, because both of them are having the pulse duration of TC by 2, got the equal time to charge up and integrate, and hence actually you will get a perfect triangular wave at the output of the adder, and at the end of the TC time period finally the adder output will be equal to 0. That is the situation when there is a perfect sync perfect sync condition is going on with the incoming signal. Now, in the second picture, we are showing what will happen if the clock starts early. If the clock starts early, then see the early gate has started early. Its duration is again Tc by 2, and corresponding to when he is coming down, the late gate has also started generating. But remember, the generation of the early pulse as well as the late pulse getting exhausted before the time of the chip is exhausted, and they are starting this much time earlier than the actual arrival of the incoming pulse. And what will happen now at the output of the fast integrator? Fast integrator is related to the early gate. So, the integrator will not get any value, will not give you any value here, because this time the pulse has not received. This is a received signal RT. Though there is no received signal, the pulse will, the integrator will start working at this point. So, he will get only this much time period to integrate. So, he can never reach to the peak value that he got earlier for the full period of Tc by 2. So, suppose I am getting Tc by 4 duration to get charged. So, I will charge half of that what I got earlier for the early gate integrator output, and the integrator output whatever is received at the end of this Tc by 2 period, then he will be holding this value till the end of the chip period. Similarly, what is going on for the negative pulse? The negative pulse is starting from here, but remember, negative pulse has got full swing. Even in this period of the negative pulse, the full period of the time both the pulses are on. So, he will be charged up fully as per the peak value that he got earlier times when the synchronization was there, and he is holding that value till the end part of the chip duration. Now, funny thing is happening at the output of the adder. Now, see and slowly the timing diagram at the output of the adder. What adder has done, from this period to this period, adder has got a positive value. Then adder has started getting the negative value, and the negative value, as the peak value of the negative voltage was higher than the positive one, definitely he will cross the 0 of the 0 axis, and he will give ending up with a negative value, and he is holding that value. So, adder output you are getting negative, some negative voltage here. Here adder output was 0. Getting adder output 0 is your target, that the perfect synchronization situation, well aligned situation. But if your clock is early, so indication will come at the output of the adder, because adder will show you that you are ending up with a negative voltage. So, what adder will tell? Then adder will tell the voltage control oscillator here, the voltage control oscillator here, to actually delay the clock, because clock has started early. So, he will delay the clock little bit. Okay. Based on the level of the remaining part of the voltage, you can also calculate the amount of the delaying required for the clock pulse. So, 1D is the example when the clock started late. So, this is a situation when clock was advanced, clock started early, and here is the situation when clock started late. So, late by this period. Okay. So, this is the output for the Tc by 2 of the early gate. Immediately after that, following that, this is the output for the late gate. Remember, now the situation is just opposite of the 1C. Here the positive integrator, the integrator associated with the early gate generator, he will get the full chance of getting charged, okay, up to here, and he will be holding the value up to this. What is happening with the negative value? This negative value is this negative one, the negative charge is starting from here, and he will be here. Actually, your charge, I mean the chip duration is getting ended. So, he will not get enough time to charge fully to the value of this one. So, he will be charged up to this value. Now, at the output of the adder is interesting to see. Adder will see the positive voltage up to this, then he will see the decrement of the positive voltage by this amount. By which amount? By this amount. So, he will actually start decreasing by an amount, but he will be ending up, as the negative voltage is less than the positive voltage here, total positive peak value of the positive voltage is higher than the peak value of the negative voltage, you will be ending up here, and this is the remaining positive voltage now you are getting at the output of the adder, who is saying that clock is late, you need to start little bit early. So, you are going positive way, means you are going late. So, you please move left, and here you are going negative, means you are going early. So, you have to make yourself late. So, now seeing the situation or the value at the of the output of the adder, the voltage control oscillator is adjusting the phase of the clock to readjust the clock's location. So, this is the way the tracking is going on in an early early and late gate based FHSS tracking. This whole description that we have done is based on the logical value 1, when where the chips are actually taking a positive voltage and they are of rectangular shape. You may need some additional logic if you try to do the same thing with the logical value 0, but that is a very trivial kind of the modification that you need to do, and the architecture almost will be same. And locally, after getting the output from the adder circuit, what this VCO is doing is they are making a back and forth within the duration of the chip. The alignment of the code is getting back and forth. I mean, the clock pulse is getting back and forth, and hence the sequence generation that is going on, that is getting adjusted inside the chip duration. But remember that even after this tracking, there may be some amount of the error. This cannot be 100% corrected all the time. So, the remaining residual error after the tracking we call the phase jitter, and which is basically the uncertainty in the clocks matching in the transmitter and the receiver, and the variance of the jitter is given by this, where your N0 is your two-sided power spectral density of the noise, and EC is the power of the chip power I should say, and this TC is duration of the chip, and in H is the number of the hops in the loop integration period, and it is a function of all these 3 parameters TC, EC, and for 4 parameters TC, SNR, and that NH. And this early gate tracking loop, fine and coarse stacking can be combined also in some cases, in some practical circuits where the coarse and fine, the both tracking both combined one can be actually moduled in a single module, as we are seeing in this circuit. Look, for our code acquisition, what we understood is, if it is a serial acquisition FHSS technique, so there's locally generated voltage control oscillator driving your NCO, and locally see the correlator, it is an active correlator, and serial search is going on. Suppose this coarse acquisition control has acquired the coarse alignment between the receiver and locally generated one, and that will be fed inside the coarse. At the same time, output of the band pass filter and the limiter can be, after linear detection, can enter into the early late gate whole structure, and at the output of this early late gate one and the output of the adder also, that will be fed into the voltage control oscillator. Voltage control oscillator is finally controlling it, and then in this loop actually the final tracking mechanism is going on. Let us look into the little bit mathematical analysis of whatever the case we have explained through the diagram. In the hop interval k, the received signal, now we are going to write, we understand this expression we have seen several times. Tc is chip dwell time, and capital R is the average power in the signal received. Nk will be the, it is a kth hop interval, so Nk is the noise process, additive wide Gaussian noise process associated with this kth interval. And remember, as we are assuming that it is having a 0 mean, so sigma square, the variance will be the power also. Eta 0 will be one sided power spectral density of this noise, and if the loop integration that we are running over the capital M number of the chips with only the thermal noise present, and we at the beginning we are not considering any interference or the jammer present, the detection probability we understand that it will be a function, it can be approximated by a Q function, where the normalized threshold will play some role, and here actually the role will be played also by the number of the search, that is the number of the tone that is getting searched over the serial mechanism. And remember that the number of the tones that you are getting searched over the tones, that is also fundamentally not only the capital M, this is also a function of your SNR, R by sigma square is going on, and this capital M is the number of the tones over which you are running the search, and gamma is our predefined threshold. So we understood that we have normalized it with respect to the noise variance, because we really wish to reduce the false alarm probability. So the detection probability will be there if the probability that the test statistics is crossing the SNR value, and it will be definitely can be expressed by the case that the probability is crossing from gamma to infinity. And tracking loop, this integration time, if I understand the chip duration is Tc, then the total time that over which the tracking loop is running will be capital M into Tc, and gamma Th will be the measure of this threshold to the noise density. Instead of gamma dashed, actually our gamma H is equal to equivalent to my gamma dashed, and tracking loop threshold it is. If this is the explanation, similarly, so the misdetection will be 1 minus the detection probability we understand. Probability of false alarm will be the taking a limit of this function over where a tends to the 0 value, and the tracking loop jitter, the phase jitter will reduce this correlation peak, because correlation peak is not perfect, because of this remaining offsets you can never actually hit, or never you can actually detect the peak. You will be, because of the jitter, you may be you are close to the peak, but this much amount of the residual error you will be ending up with. And if I consider that the jitter in which wherever you will be, if I consider that is a random variable, and it is it can be well approximated by the Gaussian, and 99.7% of the time it will be within the 3 sigma of the mean, so that the correlation peak is reduced by a factor of d, and then the d will be given by 1 minus 3 sigma by Tc square. So what we are considering here is that we are binding that the jitter we observed, that jitter will be there, the remaining offset whatever is there. First of all, it is Gaussian distributed, and 99.7% of the time, means close to just 0.3% of the time you are actually getting a miss, but for more than 99% of the time its value, the jitter's value is within 3 times the sigma of the mean. So you are within very close to each other, and then this reduced, then the peak, from peak whatever the amount you will be reduced, it can be measured, it can be given by this formula. And now if I understand that this is the way, by this factor from the peak value the signal power will be reduced. So I can actually multiply the R, which was actually the power of the received signal. You are not getting R, you are getting a fraction of this R now, and capital M is the times you are integrating over, and WIF we understand that WIF will be 1 by the threshold, 1 by the hopping time period of the first frequency hopping, and here the sigma square will be coming in the expression of capital A, as we have seen earlier, where here we have seen, but here this sigma square we have changed by a factor, there is a variance, right. So, the total power, it is a noise power also. So, we have changed it by the power spectral density of the noise multiplied by the noise bandwidth, which is equivalent to signal bandwidth also. So, A has turned to be like this. So, there are very wide variety of the control processes that can be implemented in this tracking, and recall that the goals of this tracking is to return to the course synchronization as quickly as possible. If you find there is a gross error in the synchronization process already, without entering into the tracking loop, you should go back and start the tracking mechanism, code acquisition mechanism as fast as possible. And say actually, so for control, for track, a lot of the control stuff is involved in the tracking loop, and let us consider a situation that small m out of the capital N type of the controls we are having, and m less than n detections of this sync loss out of the n passes are required before returning to the course synchronization. So, this is a one kind of a logic that we have fixed. Suppose at least m number of the detections of the sync loss we have to detect, then only we will declare that there is no synchronization has been already happened in the course acquisition mechanism. So, we need to go back. So, without seeing actually one time loss, sync loss, we should not go back. So, this kind of the logic is developed inside the FHSS tracking mechanism to detect whether we should go back or to the code acquisition or not. And refinement also is possible. I mean, how to detect actually whether m less than n, whether we will go back or not. So, in that situation what we do is we can consider a situation when we will be setting m equal to 0 upon any detection of the current tracking, and then for the last one, I mean for this kind of the one where actually at least one tracking mechanism we will continue, and we will try to measure what will be the typical mean time to loss of the synchronization. We will try to measure that quantity, where actually there is a value of q, and this measurement is given by this bigger expression, and this q, the q will be p by pm, when actually this TL is the mean time to loss the synchronization, and also known as the mean hold time when the code epoch has been correctly determined. So, there is a loss, suppose the situation is something that there is a loss, sync loss and sync correct, sync loss and sync correct, that is going on. So, for a situation when the sync lock is there, in that way, in that situation we are trying to calculate the hold time or the mean hold time for this lock, and we may put here actually the value of the q is equal to 1 minus the probability of the false alarm, which is the mean hold time for when the code epoch is not established at all. I mean there is a sync loss. So, the mean time for the false lock also the code acquisition, I mean the code tracking circuit can measure and quickly feed us give us a feedback. So, whether the hold means whether synchronization is hold, for the mean time for holding the synchronization and the mean time for giving the false lock, both can be now quantified, and based on that study also you can decide whether we should go back for the code acquisition or not. The same Russian fading model if I consider, and the signal propagation environment that we have considered earlier also given in 1.13, if I go ahead, then your then actually we will see that the parameter in the last expression, that n, q to the power n, this is the number of the times the tracking detector is running basically, and on that environment that we have already taken over the Russian channel, over the Rician channel. If I take an example, suppose it is practically found and also through the experiment it is found that for an SNR of say 5 dB with one detection of the loss of the sink adequate to reinitialize the course acquisition, the mean hold time approximately will be is found to be around log value of the mean hold time to the correspond to the TC time ratio of this can be approximately of 11, which leads us that the whole time will be 115 hours. So, if we can show actually some value for SNR of 5 dB, if we can keep a value of around close to 11. So, for 115 hours it is guaranteed that the synchronization will be hold good. So, fundamentally this is the ratio of with respect to the chip duration, what will be the how much time actually the whole time is possible to keep, and you need not to go back to the course acquisition once the acquisition and tracking both are done. And it's based on the several situation, because we have considered though it is a Rician environment, but we have not considered that the Doppler effect happening inside. We have not considered the interference, the profile of the interference, how it is changing over the network. We have not considered the other front end receiver impairments that are coming into picture, and any other change in the velocity of the transmitter as well as receiver, whether they are happening or not, hence the change of the Doppler frequency. If everything is perfect, then once you are getting it, and this is the expression that we are giving us, and we can get at SNR of 5 dB with only under the noise acting on it. For 115 hours you can keep the holding time of the synchronized situation, but this is highly actually idealistic situation. In practice we never get this much amount of the time for